Okay, next let's go to this example. We need to verify if our given function is meets the assumptions of the Rolle's theorem. In this case, we're given a rational function given by f of x equals 16 minus x squared all over 5 minus x. And the interval given is from -4, the closed interval -4 to 4. But we take note that the domain of f is set containing, the set of all real numbers except the set containing 5. This means that f is defined on all values of x except for that number that makes the denominator 0. There's a theorem that rational functions are continuous and differentiable on its domain. Also, we know that rational functions are continuous and differentiable on its domain, on their respective domains. Okay, in this case, we can say that since our given interval is in the domain of f, or is a subset of the domain of f, hence the first and the second assumptions have been met. You can say that since f is continuous on R minus set containing 5, then it is continuous over the closed interval -4 to 4 as well. Similarly, since f is differentiable on its domain and -4 to 4 open interval -4 to 4 is a subset of the domain, then it is also differentiable on the open interval -4 to 4. Okay, so we're done with two things. The last thing we need to determine is if the function values at both endpoints are the same. Let's check. What is f of 4 and f of -4? Upon substitution, f of 4 is 16 minus 16 over 1, or it is just 0. And f of -4 is 16 minus 16 over 1 is over a positive number. 5 plus 4 is 9. That's over 9. A 0 over 9 is a 0 as well. And they are the same. Hence, f of 4 is equal to f of -4. Right? Therefore, it satisfies the assumptions of the Rolle's theorem. Therefore, there exists a number c which is between -4 to 4, such that f prime of c is 0. Okay? Then we are tasked to find that value of c in between -4 to 4. Okay. Since f of x is given by 16 minus x squared over 5 minus x, its derivative, it is f prime of x equals the derivative of this quotient, we use quotient rule. For this derivative, the law is 5 minus x. So then differentiate the high, or the numerator. Derivative is -2x, low d high minus high d low, 16 minus x squared times the derivative of law is -1 all over the square of the denominator is 5 minus x quantity squared. Okay, simplifying this further, this is equal to -10x plus 2x squared. Negative times negative is positive, so plus 16 minus x squared all over 5 minus x quantity squared. This becomes 2x squared minus x squared is x squared minus 10x plus 16 all over quantity 5 minus x quantity squared. Well, the numerator is factorable as, x minus 8 times x minus 2 all over 5 minus x squared. Hence, if f prime of c is 0, if there exists such that this is true, there exists a number c such that this is true, then c minus 8 times c minus 2 over 5 minus c squared is 0. Since 5 is not in the domain of, or is not in the interval we are considering, then we can multiply 5 minus c squared on both sides. Then we have c minus 8 times c minus 2 equals 0. So we have c equals 8 and c equals 2. Well, since 8 is not in the open interval -4 to 4, then we choose c equals 2. Okay, so let's verify that the tangent line to the curve y equals arctangent x is parallel to the line connecting the graph of the function at the endpoints of the interval 0 to 1, or close interval 0 to 1. Okay, let's imagine what we are finding here. Say we have this graph of arctangent. Say this is pi over 4, this is pi over 2, this is 0, this is negative pi over 4, this is pi over 2. So we learned this from our trigo classes. Then this is an asymptote. We have an asymptote here, another horizontal asymptote here. This is 1, this is -1. We have points here. This is the graph of y equals arctangent of x. But in our case, we just need to verify that there is a tangent line which is parallel to the line connecting these 2 points. Okay, so let's connect it graphically speaking. This is what we are verifying. There is a line, specifically a tangent line, parallel to this line connecting the endpoints of y equals arctangent x in this interval. Then how do we do that? Well, if our function satisfies the assumptions of the mean value theorem, then we can analytically verify that there is a number c between 0 and 1 such that its slope is the same as the slope of this line. Okay, let's verify if the function y equals arctangent x in the interval close interval 0 to 1 is continuous and differentiable. Okay, we know that the inverse trigo function arctangent x is continuous everywhere. Hence, it is also continuous over 0 to 1. Another one is arctan is differentiable everywhere as well. Also, y equals arctangent x is differentiable everywhere. This implies that it is differentiable on the open interval 0 to 1. Very good. Then, by MVT, by the mean value theorem, as we have recalled a while ago, there exists a number C such that, merong number C na kung saan satisfy to. Or the derivative of the function evaluated at C, or in other words, the slope of the tangent line at x equals C is the same as the slope of the secant line connecting the endpoints of the interval. And take note that C should be between A to B. In this case, C is between 0 and 1. If the question really only asks for if there is a tangent line, meron bang tangent line dun sa curve na yon na parallel dito, tapos na. We already found it. Since we have shown that assumptions of MVT were satisfied, then there is a number C between 0 to 1 such that the slope of the tangent line is the same as the slope of the secant line connecting A f of A, this is f of A, A f of A and B f of B. But if we want to do a little more effort, let's try to find that number C. Okay? So we note that if we let y equals f of x, then f prime of x is equal to, what's the derivative of arctangent? 1 over 1 plus x squared. Hence, f prime of c is equal to 1 over 1 plus c squared. Then by MVT, sabi nga natin kanina, there is a number C in 0 to 1 such that this is true. 1 over 1 plus c squared equals f of 1 minus f of 0 over 1 minus 0, or arctangent of 1 minus arctangent of 0 over 1 minus 0, or arctangent of 1 is pi over 4 minus arctangent of 0 is 0, all over 1 is just pi over 4. So this equation implies that c squared plus 1 equals 4 over pi. Let's reciprocate both sides. Hence, this implies that c squared is equal to 4 over pi minus 1. And thus, c is equal to plus or minus square root of 4 pi minus 1. But since we need to find c between 0 to 1, we can omit right away that we cannot consider that negative number. Hence, we choose c equals square root of 4 pi minus 1 as a legitimate candidate. But is this between 0 and 1? Well, if you have a calculator there, can verify it. But if you can analyze what number really this is 4 minus pi all over pi. Square root of 4 minus pi all over pi. We know that pi is about 3.14. So meaning 4 minus pi is less than 1. Tama? Well, 4 minus pi is less than pi. Hence, this fraction is less than 1. This fraction is less than 1, then the entire radical is less than 1. Hence, this value of c here, c equals square root of 4 over pi minus 1, is in 0 to 1. Okay, that means if c is equal to square root of 4 over pi minus 1, then the slope of the tangent line at that particular value c is the same as the slope of the secant line passing through the endpoints of our interval. So probably our value c here is in here. Say for example this is c, then we got c to be square root of 4 over pi minus 1. Then its slope is of the tangent, then the slope of the tangent line here looks like this one, which is indeed seems parallel to our secant line. That's it.